Have you ever picked something up and just wondered, how did this get here? How did it go from just a random thought, a little spark in someone's brain, to a real thing I can actually hold? Well, today, we're going to crack open the playbook that shows exactly how that incredible journey happens.
You know, it can really seem like magic sometimes, right? But behind every single product you use, there's a surprisingly clear and structured path. So let's walk that path together and follow an idea all the way from a thought bubble to the finished item on the shelf.
All right, so every product, no matter what it is, starts right here. This is the first stage, where ideas are born, they're tossed around, and they start to get refined. To make this real, let's imagine we're creating a smart coffee mug, one that keeps your drink at the absolute perfect temperature all day long. That's our little spark.
But here's the thing, just one idea? That's not enough. You start by generating tons of them. Then comes the screening phase, where you get real and filter out the ones that are just not going to work. The best ideas get developed into detailed concepts, which you then test with actual customers. After that, you've got to do the business analysis. I mean, can we actually make money from this? Before you finally select that single, most promising concept to move forward with. It's really like a giant funnel, taking a whole flood of ideas and narrowing it all down to just one winner.
Okay, so our smart coffee mug concept won out. Awesome. But, an idea isn't a blueprint. You can't build from just an idea. To actually make this thing, we need a really detailed plan. And this is where a discipline called systems engineering comes into play, to figure out how all the different pieces are going to fit and work together. System engineering is all about seeing the big picture. For our smart mug, it's not good enough to just design a great heating element or a battery that lasts a long time. Nope, we need a process that makes sure the app talks to the battery powers the heater in just the right way, and the physical mug itself doesn't, melt. It's the discipline that ensures everything works together as one seamless, awesome product.
Now, this whole idea can feel a little abstract, so let's look at something like a drone to make it super clear. System engineering kicks off by defining the requirements. What does this thing absolutely need to do? Then, it breaks the drone down into all its little parts, or subsystems. But the real magic, it's in the integration, making absolutely sure the camera, the GPS, and the motors are all communicating perfectly so that the drone actually flies for 30 minutes and avoids crashing into things.
And as they're designing, engineers follow these brilliant little rules of thumb, or heuristics. Things like keeping the design simple and using standard off-the-shelf components. That's not just about making their lives easier. It actually reduces the cost, it improves reliability, and in the end, it makes the final product better for all of us. All right, we've got our blueprint. Now comes the really fun part, making it real. This is the stage where we go from drawings on a computer screen to a physical object that we can actually pick up and hold. This happens through a process that honestly feels like it's straight out of a science fiction movie. It's called rapid prototyping. Think of it like an industrial-strength 3D printer. And it's a total game changer because it lets engineers take a digital CAD file and sometimes in just a matter of hours, create a tangible prototype. They can finally see how it looks, how it feels, and if all the parts fit together in the real world. And get this, it's not a one-size-fits-all deal. There are different techniques for different needs. SLA uses a laser on liquid resin, which is great for super smooth, high-accuracy models. Then there's FDM, which you might have seen in desktop 3D printers. It just melts plastic filament. And SLS uses a powerful laser to fuse powders together. It's all about picking the right tool for the job. So how does it actually work? Well, it breaks down into these 4 key steps. A digital model on the computer gets computationally sliced into thousands of super thin layers. Then, a machine builds the object, one layer at a time, until a complete prototype emerges. It's literally turning pixels into a physical product. Pretty cool, right?
Okay, so we've got a prototype of our smart mug. We can hold it, it works, but we're not done yet, not even close. Now we have to test it, and all of testing really boils down to answering 2 very different but equally vital questions.
And I'm not exaggerating here. This next part is where so many amazing sounding products either find success or completely fall apart. It all comes down to understanding the 2 critical sides of testing.
Okay, so here's the absolute heart of it. This distinction. Verification asks, are we building the product right? Does our smart mug meet all the design specs? Does it actually hold 12 ounces and heat to 140 degrees, just like our blueprint says? But validation. Validation asks a totally different question. Are we building the right product? Is a self-heating coffee mug something customers actually want, and are they willing to pay for it? You see the difference? One checks against the documents, the other checks against reality.
And as you'd expect, you use totally different methods for each.
Verification? That happens in-house with things like design reviews and lab tests. But validation? Oh, that has to happen out in the real world, with field trials and by putting the prototype into the hands of actual users to see how they really react to it. So, our mug passed all its tests. We're on the home stretch. But before we hit that big green manufacture button, we gotta talk money. And I don't just mean the price you see on the box. I'm talking about the total cost of the product over its entire life.
The tool for this is called Life Cycle Cost Analysis, or LCCA, and it forces a huge shift in thinking, away from just the sticker price. It makes you account for everything: the research, the manufacturing, the shipping, the electricity it's going to use, potential repairs, and even how much it costs to recycle it at the end. It's about finding the true cost of ownership, from cradle to grave.
You want to see this in action? Just look at a light bulb. The older CFL bulb? Yeah, it's cheaper to buy, but its higher energy use and shorter lifespan mean its total lifetime cost is way higher. The LED bulb, on the other hand, is more expensive up front, but it ends up being the far, far cheaper option over time. LCCA shows us that the best deal isn't always the lowest price. And now we have to talk about something a little tougher. The hard truth is that even with the absolute best playbook in the world, products can fail. But you know what? Failure is one of the most powerful teachers in this entire process.
It's a pretty sobering statistic, isn't it? After all that work, the ideas, the design, the prototyping, the testing, a huge number of products still just don't make it. So what's going wrong?
So what's the deal? This chart lays it all out. And while things like technical glitches and high costs are definitely factors, the single biggest reason for failure by a long shot is poor market research. And that takes us right back to validation. It's a failure to answer that one critical question: are we building the right product? Most products don't fail because they're built poorly. They fail because they solve a problem that nobody actually has.
Okay, so if you walk away with just 3 things today, let it be these. First, getting a product to succeed is a structured, disciplined process, not just a lucky idea. Second, great testing has to answer both questions. Did we build it right, and did we build the right thing? And third, the true cost of anything is its lifetime cost, not just its purchase price. Look, this journey from a spark to a product on a shelf, it's complex for sure, but it's not magic. It's a playbook, a process that anyone can learn. So now that you have it, the only question left is, what are you going to build?